All right, today is going to be exciting. We get to go on a little journey of mental torture. So remember last class I was giving you some identities and we were seeing how you can do different things and, just trying to find the correct path from point A to point B. Today is more of the same. So I finished off last time with, I did that sine squared v minus 1 over tangent v sine v minus tan v. That's where we finished. All right, so now what we're going to do is continue with more examples. And the first example is going to be for us to show that cosecant theta times tangent theta is equal to secant theta. Now, we're going to start off very, very simple. This is a very simple identity. We want to show that this is true. So hopefully from last class, you gathered that when you're trying to prove an identity, that you are not allowed to work with both sides of the equation at the same time. What I mean by that is this. Like, let's say that I had x over 2 plus 4 equals 11 back in college algebra, and we were trying to solve for x. Then what you could do is multiply both sides by 2 right now, right? You could, to clear the fraction. That's what we did in algebra when we were working with equations. This is an equation, so you might think you could do the same thing, like do something on both sides. That's not the way it works. With identities, when you're asked to show something's true, you must start with one side of the equation and manipulate it into the other side. Turn it into the other side. Now you can start with the left-hand side and try and turn it into the right-hand side, or you can start with the right-hand side and try and turn it into the left-hand side. It's your choice. The rule of thumb is to pick the side that's more complicated looking, because if it's more complicated looking, there's more things you can do to it. Like this right here, secant theta, there's not a whole lot I can do with secant theta other than rewrite it as 1 over cosine, right? So this, I have more, room to play with here. So I'm going to start with the left-hand side. I write LHS for left-hand side. I write down the left-hand side. And now I do not write down equals secant theta. I'm just going to take this expression and try and turn it into secant theta. So we know a little bit about these functions, right? Cosecant is 1 over sine. Tangent is sine over cosine, right? So I'm going to write that down. This is 1 over sine theta times sine theta over cosine theta. And then you can cross out the signs. And what you're left with is 1 over cosine theta, but 1 over cosine theta is secant theta, which is now the right-hand side. So check, I'm done. That's about as easy as it'll ever get, okay? But the idea here I want to make sure you're clear on is you start with one side and try and turn it into the other. Now, as we'll see, sometimes getting from that left-hand side to the right-hand side is very difficult. So we will sometimes start with the left-hand side and work it down to something and just be like, man, that sucks. And then we'll say, all right, well, let me start with the right-hand side, and we'll start working the right-hand side, and we'll get it down to the exact same thing. And then what happens is we create like a chain that connects the two together. But that's coming, all right? Just for now, we'll start with one side, turn it into the other. All right, let's go through. I'm going to work through every example that's in the book, and then my hope is to go and just start picking some random problems out of the homework. Not homework problems, but problems similar to the homework problems. And that way, hopefully I'll come across something. I mean, I haven't done any of these before class, so hopefully I'll get to something where you'll see me kind of my thought process, because I think that's important to see, all right? So the next one, we want to show that sine squared of negative theta plus cosine squared of negative theta is equal to 1. This is a ridiculous problem. Is that really what they want? Okay. I think, I don't know why they have this as an example, but it's in the book, so we'll do it. This is one just because the Pythagorean identity. I mean, the Pythagorean identity says sine squared x plus cosine squared x equals 1, right? That's our Pythagorean identity. And x is anything. Doesn't matter what that is, but they have to be identical, all right? So whatever this is, this has to be the same. That's exactly what we have it going on here, don't we? I mean, this you could call negative theta x, and then you have it. It's done, right? Let me see if, yeah, there's really nothing to do here. There's nothing to do. Yeah, you know the identity, so yeah.
That's how you show it.
It's done. Next example. I actually hate that example now that I see it. But like I said, I didn't want to come in here prepared because then it would take away from the thought process, which is important to see. Okay, this one's a little more interesting. Okay, show that that's true. So, sorry, show. The book uses different words. Instead of writing show, they put establish the identity. That's the instructions you'll see for your homework. Establish the identity. So which side would you like to work with? Left side, right? The left side is way more complicated than the right side. So let's start with the left side. So I'm going to write it down. Left-hand side. Yes, I'm going to write it again. Okay, so I start with that. And now I am free to do as I please with that. Is the numerator the Pythagorean identity? No, because there's subtraction. And because it's subtraction, it is not the identity. Now, looking at the right-hand side, trying to foresee into the future of what we're trying to get, do you kind of see that we have cosine theta minus sine theta is the only thing left, right? So somehow this is going to have to go away, right? I don't know. What do y'all think? Any ideas? Pardon?
Multiply to the other side.
What do you mean? Yeah, can't work with the other side. See, we're working with this expression. That's all we can work with. Pardon?
Left-hand side.
Left-hand side only, yep. Remember, this is where we left off last class. Anything is okay as long as it's a legal algebraic move or you're using an identity that's true. And I told you that you may try something and it may lead you off on a path that takes you way around, and then you may do something to this that takes you further away from where you're trying to go. But you have to try something. Does anybody see anything here? I see something, but I want to see if anyone else sees something that we can do. I can't go too long with silence, so I will offer hints.
Hint me.
What do you mean?
Because there's two of the signs.
Oh, like cancel here and here? Is that what you mean? Let's ask ourselves that question with a different problem. How about this? If I have 9 minus 4 and I have 3 minus 2, can I cancel this and this? I can't, right? And that's what you would be doing, right? Look, this is please do not hesitate to do something, try something, say something, because these are the types of things that when I was a math student drove me crazy. I didn't know, I was very insecure with the rules, like why I couldn't do that. So what I would do is I would just try and give myself an example that was similar to this and see if it made sense. And I eventually got to the point where I understand it all now. But a lot of things that I looked at didn't make sense why I couldn't do things. But do you all see why we can't do that?
Yes.
Do you all see a similarity between these two?
It's
Okay.
subtracting there.
Yeah, this division bar means you have to do everything on top separated from the bottom. Yes, ma'am.
Could you multiply the bottom by negative?
Multiply this by a negative. If you do that to the bottom, you have to do it to the top. So I would say that that's completely legal. Now, what was your thought behind that? Like, what are you thinking? If you multiply the bottom by negative, are you thinking you're going to get positive cosine, positive sine, something like that?
I didn't realize we had to do it to the top too.
Yeah, we have to do it to the top also. Yes?
Is there a difference of squares?
Ah, there it is. Difference of squares.
Yeah,
Okay, do y'all see the top is a difference of squares? Yes? Now, I'm not saying this is going to get us there, okay? That's what I see. That's what I see I'm going to try, and I'm going to hope for the best. It seems promising, though. Okay, so let me try that. This is equal to the difference of two squares, and the bottom I'm just going to leave. Okay, and so what does the top become?
Sine plus cos.
Sine of negative theta plus cosine of negative theta, and then sine of negative theta minus cosine of negative theta. Does everybody see that difference of squares? You sure? Okay. Does that help at all? Oh yeah, these cancel. Now the reason we can cancel these is because we have multiplication here. And so these are separate factors. And when you have factors, you can cancel. So this entire denominator cancels out with that factor. And what we're left with is really looking pretty darn close to where I'm headed, right? Because we no longer have a denominator. But this has thetas, that has negative thetas. So now at this point you have to remember the even and odd identities, which I gave you one time very briefly in the middle of a lecture. I gave you two identities. One of them was that sine of negative theta is equal to negative sine theta. And the other one was that cosine of negative theta is equal to cosine of theta. I don't need parentheses, but I'll put parentheses. This is an odd function. It's very strange. And this is even. Are you going to make it through the semester, man? Should we should we start a GoFundMe for you?
I already got my cremation paid for, so we're good.
All right. Do those look familiar? Those are two identities that do come into play quite a bit. And I don't want to take too much time on this, but let's just see why they're true, because I think it's important that you understand them. Okay, so let's say someone gives me an angle theta. And let's say I'm on the unit circle, theta. What is cosine of that angle? Well, okay, that's an arbitrary angle. Is it the x or y coordinate? It's the x coordinate. So do you agree that this is cosine theta and this is sine theta? Whatever theta is, right? This is a unit circle. I didn't put 1. I'll put 1 to be thorough here. Then the x coordinate is cosine of the angle. The y coordinate is sine of the angle, right? Now, what does negative theta look like? It's that angle theta, but down. It's going to be down in the fourth quadrant, right? So this is negative theta. Negative theta. And do you agree that they have the same x coordinates? Okay, so do you agree that this is cosine negative theta? These two match each other, regardless of what theta is, right? This distance is equal in both of these scenarios. Now, does the same apply for the sine? The y-coordinate is this height, right? But if I do negative theta, it's what? It's not that, it's reverse, right? It's the negative of that. And that's what this one is saying. This says, look, if you plug in theta for cosine, you get the same as what you get if you plug in negative theta. This one is saying, if you plug in negative theta, it's the same as sine of theta, but they're off by a sign. Those are the even and odd identities for sine and cosine. So how can I use that now? What is this, according to the odd property? This is negative sine theta. And then what is this? Just cosine theta. And this is the right-hand side. Isn't it? It's just changed the order, but it's the right-hand side. So I got it to turn into that. All right, so that one had a little more meat on its bones. Let's see if we can establish this next one. If you like puzzles, this is your section. I didn't, when I was learning it, it drove me crazy. This whole thing drove me nuts. But now that I am trying to help you all become whatever it is you want to become, engineers and computer scientists and stuff, doctors, whatever it is you want to become, these problems are probably the most relevant to you because they're problem solving. This is problem solving. This is you with no template. You can't copycat some formula. You can't just be like, oh, anytime I see that, I just do this. And in the real world, that's the way it works, okay? You're an engineer working for a firm. They hand you a problem, and you can't just go into the other office and be like, hey, where's the key to that problem? Like, let me, show me an example of that worked. It's not it. You have to solve the problem, right? So I think these are the most important types of questions we ask in a class like this. Show that this is true. So which side do you want to start with? Left. Yeah, let's go with left-hand side. And 1 plus tangent u over 1 plus cotangent u. We're trying to turn that into tangent u. Are you kidding me? All right. I'm all ears, whatever you want, as long as it's legal. Now, some of these problems, you just have to see them, someone do them that first time to kind of be like, okay, that's something I can try in the future. Almost like a bag of tricks, Oh, we can maybe pull out that trick for this problem. There is kind of a fallback if you ever get really hung up. It's kind of like your last resort type thing, but it won't always work. But if you're really stuck on something, just get everything in terms of sine and cosine. Just get everything to sine and cosine, and hope for the best. But I'm not willing to do that yet unless we all want to do, we're all ready for that. So does anyone see anything?
Tan could be sine over cos, and cos could be cos over sine.
Okay, so we can rewrite that as sine over cosine. We could rewrite that as cosine over sine. But other than that, is there anything else? Like no difference of squares, no Pythagorean identities? Pythagorean identities, you need squareds, right? You need squared trig functions. We don't have that. Can I just square everything? Can I just take the whole thing and square it? You may not, okay? Now, if you had an equation, you could square both sides, but you can't just arbitrarily take something and square it out of nowhere. That changes it, right? Like if I give you, hey, everyone, there's the number 2, and then you just say, hey, I'm going to square it now. It's no longer 2, right? It's 4. So you cannot do that. Sine, cosine, I guess? Yeah? Yes?
Change 1 to like sine over sine or like cosine over cosine.
Oh, sure. Yeah. Could you change the 1 into sine over sine or cosine over sine? Cosine over cosine? Yes. Yeah, absolutely. Now,
So we can like add them?
yeah, you could rewrite that 1 however you want. You could rewrite it as tangent over tangent. It's really up to you. I think before we do that, let's try this as sine over cosine, and this one is cosine over sine, just to see. That might help motivate what we do next. All right? So I'm going to rewrite this as 1 plus. Now I'm going to have, this is called a complex fraction. It's just a fancy word for saying we've got fractions within fractions. All right, now can I take this fraction, just flip it up like this, up to here?
Yes.
Just this one?
No.
No. Okay, because the ones are added, right? So again, part of this is not only trying to show you what you can do, but the things you can't do. Yes? Yes, we could have turned this into a 1 over tangent. We could have done that also. That would have been fine. We could have turned this into 1 over cotangent. Either way. But I'll stick with this. Get a common denominator? Where? Up here? And then down here? We can try it. Now, that would be the same thing as you turning that 1. In this case, you're going to need to turn this 1 into a cosine over cosine, and this one to a sine over sine, so that they all have the same denominators. That's the same thing as getting a common denominator. So let me do that. So I got a common denominator on the top. Everyone understand why I did cosine over cosine on the top, but on the bottom I'm doing sine over sine? Is everyone clear on that? Okay, let's put the tops together. When we do the top together, we're going to have cosine u plus sine u over cosine u. And on the bottom, we're going to have sine u plus cosine u over sine u. So what we've effectively done is we've made it, remember a second ago I said, can we flip this fraction up? And we said no, because it's got the plus 1 attached, right? But by getting a common denominator and pushing these together, now you have one fraction divided by another fraction. Now you can flip, can't you? You can flip this. And a good thing is about to happen when we flip it. We're going to have the top fraction, cosine u plus sine u, over cosine u. And then when we bring this one up, division becomes multiplication of the reciprocal, sine u over sine u cosine u, plus cosine u. Let's see where I am here. Do y'all see what happens? What?
Sine u, cosine, plus cosine u, and sine.
This right here is its own factor, and this right here is its own factor because they were separated by multiplication. And they're the same, right? Even though they're different order, they're the same expression. And so we can cancel those. And then you have sine over cosine, which is tangent. Sine u over cosine u, which is tangent u. This is the right-hand side. We're done. Do you want to work it a different way just to see if we could get it a different way? Or do you all care? Okay, let's do it. Let's do it. I just want to, just for the sake of showing you that there's more than one path, instead of doing sine cosine, what if I left this one as tangent u, and then this one right here, instead of cotangent, I put 1 over tangent. Who had suggested that one? Someone suggested that. Okay, so let's do that one instead and see if we can get to here, all right? So what I would do at this point is I would still get a common denominator, but just on the bottom, all right? So let's see what happens. I would have 1 plus tangent u over, now what am I going to need to turn this 1 into? Tan over tan. So I'm going to have tangent u plus 1 over tangent u. Is that all right? I got my common denominator, and I put them together all in one step. Is that okay? Now what? You flip it. Now, I want to make sure everyone sees this. The numerator is really this, right? That's really the numerator. 1 plus tangent u is really 1 plus tangent u over 1. So I can look at it as a fraction over another fraction. And if you look at it that way, then you can flip this. And then that would become 1 plus tan u over 1 times what? Tan u over tan u plus 1. And then what? They cancel. This factor, cancel, and you're left with tangent, which is the right-hand side. So that worked. Questions? Okay, let's do another one. You didn't realize today would be this much fun, did you? And we're not done. We have a lot of time. So let's see here. Sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine theta is equal to 2 cosecant theta. We'll start with the left. Okay, I'm going to do this a little different now. I'm just going to work this. All right.
You could get a common denominator first.
You mean try and put both those fractions together into one big fraction? That's fair? Y'all willing to do that? Okay, if we do that, what are we going to need? What are we going to need to introduce on the top and bottom here? Sine theta and sine theta. And it'll have to multiply. There's two terms there, so it'll be something like that. And then here I have to introduce a 1, right? So the other denominator, 1 plus cosine theta over 1 plus cosine theta. Is that all right that I'm doing that? I'm trying to save some time and space. Is that all right? I'm getting my common. All right, let's go ahead and put this together. So I'm going to do sine times sine, right? So sine squared theta over, now on the denominator, I would technically need to distribute the sine through, right? Or I could leave it as sine with the parentheses and just leave that whole thing down there. It's kind of up to me, right? Do y'all care? I'm going to leave the sine out for now. So I'm going to leave this sine out. And I'm going to have 1 plus cosine theta. Now that's my common denominator. I need to now, this numerator needed to add, right, together with this numerator. Agreed? And I've got to multiply this times this, and there's two terms there, so it's actually, I'll put it here like this, plus, it's 1 plus cosine theta times 1 plus cosine theta again. Do y'all see that? Yep, the algebra here is okay? Can we cancel one of these?
No.
No, can't do that because we have two terms on top. If we cancel one of these, we would have to have one of these over there also. So you are not allowed to cancel one of those. So what do you think?
Expand.
You want to expand. Good, that's the correct way to say that too. When you multiply two things together, it doesn't matter if it's binomial, or trinomial, it doesn't matter. When you multiply things out, FOIL is the cute name. expanding is the correct terminology for this. So we are going to expand this. I don't like cute names. I don't like cute things. So we'll go with expand.
1 plus 2 cos theta plus cos squared theta.
All right, so we have sine squared theta is still there. We've got 1 plus 2 cosines of theta
Plus cos squared theta.
plus the cosine squared. So when we did the expansion, we actually had when we did this expansion, we actually had 4 terms, but we collected like terms in the middle, and that's where this 2 cosine theta comes from. Forgot my parentheses. Ugh, okay.
Sine squared theta plus cos squared theta would be 1.
Ah, this right here, these two together, if I rearrange that, that's a 1, isn't it? Everyone see that? Sine squared theta plus cosine squared theta is 1. So now I have 1 plus 1 plus 2 cosine theta over sine theta times 1 plus cosine theta. 1 plus 1 is 2. 2 plus, pardon?
Sine squared and cosine.
Sine squared theta plus cosine squared theta. These two together is a 1 through the Pythagorean identity. Sine theta, 1 plus cosine theta.
Backward the 2 and then you can cut off 1 plus cos theta.
If I pull a 2 out of both of these, I'll be left with 1 plus cosine theta, and it's going to cancel with this bottom factor. And then I'll be left with 2 over sine, which is 2 cosecant. So I'll finish this up. We're there, basically. So we have the 2 comes out on top. We have 1 plus cosine theta. And then on the bottom, we have sine theta. And then 1 plus cosine theta. These factors cancel because there's multiplication there. We have 2 over sine, which is 2 cosecant theta. I'll write it like this. It's 2 times 1 over sine, which is 2 cosecant theta, which is the right-hand side. Check. I love these problems, but I hate grading them. These are not fun to grade. You want to write out as much detail as you possibly can when you take a test on these so that if you do make a mistake, I can find it easily. If not, you lose more points if I can't make sense out of your work. The good news, though, is when you take a test, you'll know if you got it, right? Like you'll know if you got it right because you'll get to the right-hand side and you'll be done. What do y'all think so far? What's your feeling here?
Trial and error.
Trial and error, yeah. You got to try something, right? I said last class, be prepared to fail more times than you succeed with these. But it's fun, right? All right. Tan V plus cotan V. Tangent V plus cotangent V over secant V times cosecant V equals 1. This is multiplication here. That's addition. So we'll start with the left side, all right? And I won't be lazy. I'm going to write it all down again. Well,
Multiply each side to get a common denominator.
what do you mean common denominator?
Multiply cosecant by secant. You did the last problem or no?
Well, I'm okay with getting a common denominator if I saw two fractions. I don't really see two fractions that I'm trying to put together.
So it's, okay. Well, this is multiplication.
We could take everything in terms of sine and cos.
This might be one of those problems where we want to just get everything in terms of sine and cosine. So you start eliminating things like you don't see difference of squares, you don't see Pythagorean identities. Let's just go for it. I mean, what's the worst that could happen? We crumble up the piece of paper, we start over, we change our major. Okay, that's the numerator rewritten, right? The denominator rewritten, you want me to do denominator in terms of cosine and sine also? I'll do that. I'm happy to do that. 1 over cosine v times 1 over sine v. That's what secant times cosecant is. So now I'm willing to do the common denominator now because I see two fractions on top. Okay, so I'd be willing at this point to do that. So we get a common denominator between these two. I'm going to have to introduce sine on top here, right, top and bottom, sine v over sine v. Over here I have to introduce cosine v. And do you already see what's going to happen? Sine squared plus cosine squared. That's going to be a 1 up there when we're done. So here comes my introduction. Sine v over sine v. No, that's not it. That was supposed to be the cosine. Cosine v, here's sine v, sine v. So my new fraction is sine squared v plus, so that's these two multiplied, plus these two multiplied, cosine squared v, over the common denominator, which is sine v cosine v. All of that over, big division bar here, 1 over, can I just write 1 over cosine v, sine v, or yeah, it doesn't matter which order. That's the same, right? If I multiply these two fractions, you just go straight across. So yeah, this is going to be 1 over, because that Pythagorean identity up there, sine v cosine v over 1 over cosine v sine v, and those are identical, aren't they? This is the same as this. I mean, the orders change down here, but they're identical. This is 1. Right-hand side. Check. And we're just cruising through this.
On the top there, you turn it on the Pythagorean identity.
Yeah, this one right here, this is going to be 1. And then these two are exactly the same. Now, you could flip it and cancel. I mean, any questions here? How many are what? I'm about to give you the last example. And then what we're going to do is we're going to pair up, and I'm going to force each group to do a couple of problems, and y'all are going to work on the boards. And then after you're done, you're going to try and explain to all of us what you did. Okay? It's going to be a fun day. It's a fun day. All right. Next one, 1 minus sine theta over cosine theta equals cosine theta over 1 plus sine theta. Now, this is the first problem that I've given you where one could argue that the left-hand side is more complicated than the right, and someone else might say the right-hand side is more complicated than the left. It's not obvious which side to start with, and there's absolutely no wrong way to go here. You pick one and you go with it and you try. All right, so which side would you like to start with?
I would go left.
You want to go left still? You okay with that? Fine with that. Left-hand side. Here we go. 1 minus sine theta over cosine theta. Now look at what you're trying to turn that into. Any ideas? You can't turn everything in terms of sine and cosine because that's already been done. So there's not that. I'll let you all think about it for a second. Anybody have an idea? Have y'all ever seen Saving Private Ryan? The very opening scene is very graphic, right? These, what are they called? Those transport boats that drop all the guys off on the beach. What are those called? Yeah, those. Yeah, so got all these guys in this, basically this big metal bathtub going up on the beach. You know, they drop the door. Somebody's got to go, right? I mean, that's kind of where someone's got to do something here. Who's going to be the first one out? You know, you may not make it, but someone's got to be the first one out here. Give me a legitimate algebraic move, and we try it. You know, we go for it. See what happens. So I'll push you, okay, because I'm ready to get on the beach. Push. All right, so look, where are we trying to get to?
Can we change one to
So look at the right-hand side. Tell me what is, I guess, missing on our side that needs to be on the right, that's going to need to be there? I'm going to need a cosine on top. So, I mean, I could multiply the top and bottom by cosine, couldn't I?
Yeah.
All right, that would be legitimate, and it would make some sense, wouldn't it? To multiply top and bottom by cosine, because I would get a cosine up top.
Probably just turn the 1 into cosine over cosine.
Do what?
Turn the 1 into cosine over cosine.
Turn this into cosine over cosine?
Yeah.
We could do that. Then we would probably need to put those two together, right, with a common denominator?
Yeah.
Okay, that would be legitimate. Look at the right-hand side again. What else? You said the cosine was missing, and I said I'd come in cosine top and bottom. That would take care of that. But what about the denominator on the right side? 1 plus sine theta? Could we make that appear? What would we have to do on the left-hand side if we wanted to get a 1 plus sine theta on the bottom? Just force it. What do you need? You need 1 plus sine theta, right? Okay, so I could force it on the bottom, 1 plus sine theta, but I would have to do the same thing on the top, right? So I could multiply both sides, or top and bottom by cosine right now. I can multiply both sides, I keep on saying both sides. I can multiply top and bottom by 1 plus sine theta. I could do I could do both of them, right? So I just gave you two legitimate moves. You want to try cosine? Let's go for it. Seems like the easiest. All right, here we go. Multiply top and bottom by cosine. Top by cosine theta, bottom by cosine theta. It's going to have to distribute up top, right? So should I distribute it? I don't know if I should distribute it. I'm not going to. Why do you think I'm not going to distribute it?
Because of what happens over time.
Because I want that by itself at the end, don't I? Like if I'm going to want this cosine theta by itself. So if I distribute it through here, it might start getting mixed up with other stuff. So I multiply top by cosine. What about the bottom? Cosine squared theta. Okay, well, I've made the cosine appear. Great, wonderful.
You could turn the cosine squared theta into 1 minus.
All right, good. So we have the Pythagorean identity, the all-important Pythagorean identity. And on the bottom, I have cosine squared theta, don't I? So if I take this identity and solve for cosine squared theta, I'm going to move the sine squared theta to the other side, which means that this identity is equivalent to 1 minus sine squared theta. So I could replace the bottom with 1 minus sine squared theta, couldn't I?
Yeah.
Why would I want to do that, though? That seems like I'm making it more complicated than it already is. Why in the world would I want to do that? That seems ridiculous. It's not, but
Isn't that a difference of squares?
that's a difference of squares. And because it's a difference of squares on the bottom now,
You can cancel.
I'll be able to cancel a factor. This is 1 plus sine theta times 1 minus sine theta. Made it. I don't mean to try and equate us solving an identity in 2017 with some guys landing on a beach in Normandy in World War II, okay? This is not the same level of intensity, yes, okay?
I was going to say you're insulting me. I'm just
Yeah. I don't want to hurt people's feelings. You know how it is. 2017, you just about can't talk nowadays.
You got to text it to
You
me.
got-
Run it through a PC filter.
All right. This is nice. This worked, right? Do y'all see it?
Yeah.
This cancels. And you've got it. That's it. Cosine theta over 1 plus sine theta. Wow. Any questions on that? Yeah. Oh, I thought you were raising your hand. It's a good question. What do we have? Do you think it would have worked had we not done cosine and would have done 1 plus sine on top and bottom? It would have actually worked. Yes.
Can you do one, or is there one where you wouldn't be able to do anything? Like, it would be undefined.
Well, if you're given an identity, that means it's true, and that means there is a path. Yeah, I mean, I guess no. I can't give you an identity that we can't do. Well, not in terms of this type of thing, this type of identity. Some identities are hard to show. Well, no. All right. Are you ready to go at this on your own in groups for a little while? Okay, let's go for it. Now, I'm going to pick some problems, random problems. And again, I haven't done these, so I'm not sure what difficulty level they're going to be. You're just going to get kind of randomly assigned. Now, let's see. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 22. We have an exact even number of people. I want to break up and partner in twos. Twos and twos only. So I'm sorry if I'm going to have to pull you away from your comfort zone. You might have to meet someone you don't know. Are we ready? Get your pair, get your partner. Everybody ready?
Make eye contact. Quick.
Okay.
Make eye contact.
If you want, you can exchange cell phone numbers and text each other instead if you don't want to talk to them.
Oh, you can't do that.
That's right. You can't. Very good.
Bonus points.
All right. Are y'all set? Okay. Here we go. So I'm just going to tell you, does everyone have a book or no?
See?
Nobody has books?
It's on my laptop. I have it.
You have one. Okay, anyone have book? Who has a book? One book here. You have a book? Pull that book out. Okay, you can bring it on your laptop. That's fine. You have the same thing? So what, just this table and this table are the only tables that don't have books? Okay. All right, so here you're going to do number 27, page 641. Okay, so this group, you're doing 27. Write this down because I'm not going to remember it. 27, 45, 62. Okay, this group, 28. This 28, 46, 63. That group, 29, 47, 64. Good? Here, which two here? Okay, you ready? 30, 48, and 65. You two are going to do 31, 49, and 66. And then which two here? The two there. 32, 50, and 67. And you're going to do 33, 51, and 68. These two, 34, 52, 69. And then, which two here? 35, 53, 70. And then let's do 26, 44, 61. And did I get you guys yet? Okay, and then this group here, 25, 54, and 71. You can use that one. Pardon? Yes, y'all can use the board. I would like for you to use the board, but if you want to work together a little bit first, you can. Whatever you want, whatever makes you feel more comfortable. All right, you just need a book, right? Okay. Yeah, you know what? Why don't you just go take a picture of it? Someone go take a picture off that book.
Cotangent U and
Okay, there's plenty of markers up here. There's erasers. Feel free to have fun. I think I'm going to stop recording because there's really no need for anything else.